Now, from Rolle's theorem, we can get another one of the most important results in differential calculus, which is the mean value theorem. It says, suppose f is a continuous function in closed AB and differentiable in open AB. Then there is a c, okay, in that open interval, such that this thing is true. F at b minus f at a is equal to the derivative at a c divided by b minus a. Okay, the graphical interpretation of this is that suppose we have this right function f, right, at a and at c and at b. Well, if we compute the difference between f b minus f a divided by b minus a, as we talked about in the first video in this unit, this is just this difference, right? This slope. Okay. Well, what this is saying, so this is the slope of this line, right? What this is saying is that there's a point C in which the derivative at this point is the same as this line, right? So, for instance, this point here. Okay. And this is true as long as these hypotheses are met. Okay. The proof of this uses Rolle's theorem, applying this to this function. Okay. And then if you check that, you will see that g at a it will be the same as g at b, right? And then you can check that this function is continuous. It's also differentiable in the interval. And then you need to check that the fact that there's a g a value g such that g prime at c is 0 implies this result. Okay. So I'll leave you to do it on your own. Okay. Practical consequences of Rolle's theorem, okay, is that we can characterize the behavior of a function in an interval depending on the value of its derivative. Okay. So supposing that the function is continuous in closed AB and differentiable in AB, we can say these things. If the derivative of x is 0 for all the values in the interval, then f is constant. Okay, not only the other way around, right? If f is constant, we know that f prime is 0. Well, the other way around works well, right? If a derivative is 0 for all the values in the interval, then the function is constant in that interval. And the proof for this is easy, right? If we write f y minus fx, where x is smaller than y, and these two guys are between a and b, right? Then we write using the formula from the mean value theorem, right? Now, if f prime is 0, that means that f prime is 0 for all c in the interval. That means that f at y equals f at x for all x and y in this interval. So that means that f is constant. Okay. Now, the second application is that if the derivative of f x and the derivative of g are the same in a whole interval, then these functions will be the same but separated by a constant in the interval. Okay, and you just need to apply this first part to a function. Let's call it h. It's f minus g, right? Well, if we call this is part 2. H prime, right, will be h prime minus g prime, right? Well, if h prime is 0 for all x in the interval, right, then that means that h is a constant k. So that means that f is g plus a constant. Okay. And if the derivative here is 0, that means that these two derivatives are the same, which is what this is saying, right? Now, for the third part, if the derivative is positive in all the interval, then f is strictly increasing, right? Again, applying this f y minus fx equals f prime times y minus x. If f is positive, this is positive, so this is greater than 0, so that means that f at y is greater than f at x, so that means that this is strictly increasing. And the same applies for the negative derivative. Okay, so if the function has a negative derivative in an interval, it is strictly decreasing. Okay.